Okay, today we completed our discussion of the energy equation. I just want to kind of give you the broad overview. The main application that we're going to be talking about is flow in a conduit. As I've sketched here, where we have constrained flow, volumetric flow rate Q, and since there's no inflows and outflows and the conduit is filled, Q entering is equal to Q exiting. That's mass conservation. Now let's suppose that we wanted to analyze a control volume that extends from face 1 on the left to face 2 on the right. Now I've placed face 1 on the upstream end, and so we have flow entering our control volume across face 1 and exiting across face 2. In this, with this setup, we can think about the energy conservation equation on the control volume, accounting for the fluxes across face 1 and face 2. After assuming steady incompressible flow, we arrive at a simplified form of the equation where we think of energy in units of length, or the head. And in that, with that construct, the energy equation looks a lot like our Bernoulli equation, that P1 over gamma plus Z1 plus alpha 1 V1 squared on 2G plus any energy that's added by pumps is equal to the conditions at location 2, pressure, elevation, kinetic energy, as long as we account for energy that's lost to turbines and energy that's lost to friction. Comment on this last term here. This is the head loss, which you can think of as friction. In inviscid flows, that would be 0. We have the energy that's lost to turbines. We have the energy that's added by pumps. Finally, these factors alpha are essentially integration factors or correction factors that account for the integration of velocity cubed over the cross-section. I refer you to the lecture notes for the details on that. But hopefully what you can see is that we have the remnants of our Bernoulli equation here, as long as we account for changes in energy due to external interactions, changes in mechanical energy due to friction, and then these correction factors that account for the velocity structure in the cross-section. If we additionally add inviscid flow, then the head loss equals 0. If we say no pumps or turbines, I'll just say HP equals HT equals 0. Those two terms go away. And finally, along a streamline, if we constrain our analysis to flow along a streamline instead of a case of a closed conduit, then alpha 1 equals alpha 2 equals 1. And with those restrictions, the energy equation reduces to P1 over gamma plus Z1 plus V1 squared on 2G is equal to the same quantities at location 2, P2 over gamma plus Z2 plus V2 squared over 2G. So that's the Bernoulli equation. Notice that the assumptions that we applied for the Bernoulli equation, steady flow, incompressible flow, inviscid flow, along a streamline, all reappear here. So we make the same set of assumptions and we arrive at Bernoulli equation. But now the form of the energy equation that I will just circle in green here can account for other changes in the energy due to external interactions, frictional losses, and even the details of kinetic energy fluxes. So the equation boxed in green is our general energy equation, which can reduce to the Bernoulli equation under special conditions.